So I want to just make some clarifications on the use of this equation for for EA effective and GIP effective. So let me tell you a few things about this effective section stiffness. Okay? So this works both in axial loading, where we say EA effective is E1, A1 plus E2, A2, and if we had more material, it would be plus E3, A3, and so on. And in shear, where we say GIP effective is G1, IP1 plus G2, IP2 plus so on and so forth. Okay? You must understand what this means. These are functions of X. These are the properties at section X. What this means is that if I have a shaft or a bar and I want to know what the section stiffness is at X, I look at X. I go and slice the bar or the shaft at X. And I look at the composition of the shaft at section X. So I go here at section X, and I look at it. I look at the cross-section. And the cross-section may be composite. Maybe the cross-section has two materials. So that this one is material 1, and this is material 2. And at section X, I find EA of X equal to that stuff, E1, A1, plus so on and so forth. And I find GIP of X equal to G1, IP1, plus, et cetera, et cetera. That equation there applies for the materials and geometry at section X. Okay? Why am I giving all this emphasis to this thing? I'm giving this emphasis because in our first quiz, we had a bar which was made of two parts. Was made of two parts, and this part here on the left, so it was not homogeneous, but it was not homogeneous not in the sense that the sections were made of composite material, more than one material, but in the sense that the bar itself was made of two material. There was one side of the bar, which had E1 area 1, and there was another side of the bar, which had the same cross-section, E2 equal to A1, but it had a modulus, E2 equal to 2 times E1. The fact that in the problem there are characters called E1, A1, E2, A2, doesn't mean then that the GIP effective, so wrong for this problem does not mean that GIP effective, that EA effective or GIP, whatever you're doing for the problem, EA effective is not. So this is this statement that the EA is E1, A1 plus E2, A2, or as somebody calculated, 3 E1A. This thing is totally wrong because on no section I have both this and this together. That would be the model, that would be this property that I would have if I put both sections together to work together to carry the load. If I had a section made of both of them together, like this, attached, and they carry the load like that together, you would have that. But the fact that you have one part of the section here that has one material and one part of the bar here that has a different material, it simply means, so that's wrong. No, do not do that. And it's important you understand this. Going forward in torsion, we're going to have bars which are one part made of one material, one part made of another material with different geometry. You do some things along X because these are the properties at X. You slice at X and you see what's going on at X. So in that case, the correct thing to do would be EA effective or GIP effective would be different here and here. So in this part here, there would be E1A1 for 0 less than x less than L over 2, or there may be G1 IP1 for 0 less than x less than L over 2. And on the other side, on the other half of the bar, there will be E2A2 or G2 IP2 for L over 2 less or equal than x less or equal than L. Okay? So the fact that you have two materials, it means that your GIP is not constant along x. It changes. It's something up to here, and then it's something from here to there. But it doesn't mean that just because you see E1, E2, E1, E2, you say, oh, I know, it sums up. It sums up if they're on the same section. Okay, one set of problems. Another problem. Another problem has to do with the intense degree of complexities to which you go when you calculate distributed loads and the resultant of distributed loads. And I do not understand well this thing. So let's talk a little bit about distributed loads. And now to get started, because you have it fresh in your mind, let's do axial loading. Okay, so distributed loads in axial loading. The little fx of x, this is force in axial loading, force per unit length. So this is somebody comes to you and saying, I'm applying along this bar 2 newtons per each meter of the bar, 1 newton per meter of the bar. So in order to find the force that corresponds to, you multiply by the length. But fx of x stays force per unit length. So for instance, say that I have a bar like this, and I'm applying an fx of x that is big here and small there. Say that it goes linearly, like that. So if this is my axis x, I'm going to have an fx that just goes like that. So this is my fx of x, right? So this would be something that goes fx of x is equal to a maximum value here. So I need some function that is linear with x, so it's going to have a linear dependency on x, so I need a minus in front of x. When x is 0, I get B0L, which is the maximum force per unit length that I get. So B0L is, so this one here, the units of this must be Newton per meter. So if this whole thing is Newton per meter, then this thing must be in newtons per meter square, so that when I multiply by meter, I get a force of whatever it is, B0 times L minus x. Okay, so now if I want to figure out what is the axial load at some section x, so this is my section x. I want to find what is n here, in this section here of this bar. This is my bar. I want to find what is n of x. What do? I cut like that. Here I have fx of x. Out of this comes my n of x. And I find my n of x equal to the integral of what is acting on this thing from here to there. What if I am holding the bar there? What am I fighting? I'm fighting the load on this part of the bar. I'm fighting this load here. You see? So this thing that I'm fighting is the integral from where I am to the end of the bar of B0 times L minus x in the x. Now, for some mysterious reason, once you get to do these integrals, you get totally lost with bounds, minus, x, plus. Go back to the basics if you get lost. Think of what this means. What is this? This is the equivalent load, the equivalent load that comes from this f of x on this chunk of the bar. What is that? It's the area under this curve, this area from where you are to the end of the bar, this thing. This is the equivalent load, is the area. If you get lost in integral, look at the area of these triangles. What is this base of the triangle? If I'm at x and the whole length is L, how much is that? L minus x. I see you're frustrated. What is the height of this triangle? Well, that's the function. B0, L minus x. What is this area? That's going to be B0, the height, L minus x, B0, L minus x, times the base, which is L minus x again, divided by 2 because it's a triangle. You can do the integral. I'm not against integrals. I like integrals. But for goodness sake, you cannot get lost on something like this. If you get lost in the integral, to make sure that the integral is correct, think physically. What you're finding is the equivalent load of the distributed load. Find the area under your distributed load. That's your integral. OK? Does that help? Stuff you know, you get lost sometimes, though. So I'm like, oh, my God, I did all this for axial loading, and we're doing torsion. It doesn't matter, because look, I can turn this into torsion with a few cosmetic changes. This one, I put 2 arrows on top. This one is not Fx anymore. It's T. And this is torque per unit length. If that's torque per unit length, then this is T, T of x. Then these units that I want Newton times meter per meter, which is newtons. To get newtons there, here I have a B0, which is Newton per meter, right? Just change the units, change your little hats. This diagram is not F anymore, it's T. And what comes out of this, I have to put double arrow because these are torques. And what comes out of here is also double arrow because this is your torque. What I calculate this here then is torque. And guess what? Everything else stays the same. Boom. Done. OK? So integrate by integration, if you know how to do it, which is be nice. If you get lost or you're not sure of your answer, think physically, think areas. OK? OK. One more clarification. Do you guys have any questions on this? No. We're going to do one more clarification, and this clarification is about angles. Angles. Phi versus gamma. OK? Somehow, because in torsion we deal with angles, and there are 2 angles in the story of torsion. There is gamma, which is the shear strain, and there is phi, which is the rotation of the sections. Both of them are angles. And because both of them are angles, sometimes you guys get them confused. But don't forget the physics of what these things are, right? So let's do a simple problem in which you just have a torque at the end, Q. And let's say that we do a problem with constant cross-section of radius r. We have constant torque there because we only have a torque Q at the end. We have one material G, so everything is simple. So because of this, then what else is constant is d phi dx is constant for this problem. Why? Because d phi dx is T over GIP effective. The torque is constant. GIP effective is constant. So d phi dx is going to be constant. OK? So I come to you, and I tell you that for this problem, d phi dx is 1 degree per centimeter. Okay? First of all, what is phi? Phi of x is, if I take every section along the length of this shaft here, and if I look at this section here, phi, and this is section at x, phi of x tells me how much the section at x is rotated. It is the rotation of the disks along the length of the shaft. That's phi. I walk along the shaft. How much did you rotate? Phi of x. I walk to another x2. How much did you rotate? Phi of x2. So if my d phi dx is 1 degree per centimeter, it means I'm here, I'm rotating this much, I walk an extra centimeter. That new section has rotated 1 degree more than the section before that. And keeps going. Every centimeter, I rotate 1 degree more. You see? So that's phi of x. Say that the length of my bar is 1.8 meters, which is 180 centimeters. I start with phi of 0. Every time I walk a centimeter, 1 degree, 1 degree, 1 degree. If there was a line up here, now this line would look like that. And this amount of phi is how much each section is rotating. You see? This angle from top to here, from top to here, from top to here, is how much this section here is rotated. Do you see? At the end of the bar, phi of L is going to be 1 degree per centimeter times 118 centimeters. So what is going to be? Come on. Yes, 180 degrees. So my phi of L at the end of the shaft is a lot. Phi of L can be big. You can have big rotations because they build up as you walk along the shaft. Phi can be very big in 201. There is no limitation on how big phi can be. What is more? What is gamma now? Gamma, the shear strain. Gamma is, if you go there and you have the line that used to be straight on top and now is rotated around the shaft. If I go there with a pen and I make a line straight along the shaft and I measure this angle here between the line along the shaft that has rotated and any horizontal line on the shaft, this angle here, that's gamma. Okay, so if my line was on top and then the shaft rotates and my line gets to the bottom, if I measure the angle between this line that has rotated and any horizontal line, that's my shear strain gamma. What is the equation for the shear strain? That's equal to the radius times d phi dx. Say that my shaft has a radius of 1 centimeter. Then my maximum gamma on the section, which is the gamma max, which is at the radius equal to the big radius, is big radius times d phi dx. If r is 1 centimeter, I get only 1 degree. So my gamma, my shear strain can be small, tiny, while my rotation angles build up and can be 180 degrees. They are two very different angles, you see? Okay. And you see that in 201, we normally deal with long and slender structures. So typically, your radius is much smaller than the length. That's why you can have typically large phi and small gamma. This stuff also applies to small short shaft, in which case you rotate more or less by the same amount of angles as the shear angle. But I just want to make sure that you understand the difference between gamma and phi.